Yes, this session we are going to discuss current electricity. Yes, cbse third chapter. Yes, so current electricity. The first few definitions are there, basic things are there. We must know that one is called number density. Number density is generally denoted by small n. Number density means number of free electrons per unit volume of the conductor, that is n divided by area into length. And while you are using this expression, kindly remember the number of electrons in the given amount of the substance or given mass of the substance can be calculated by this expression n Avogadro, that is equal to mass given in gram divided by a molar mass of the substance. This is the basic one. And next, what we are going to discuss an important 3 or 5 mark category question, concept of drift velocity. Yes, so in 10th standard you may study that current is nothing but rate of flow of charge. In what manner the charges or electrons in the conductors are in motion, that can be discussed in this session. Okay, now our aim is to find out a derivation for drift velocity Vd vector. Yes. Now please consider the situation where the conductor has of length L and area of cross section is A. If there is no external field, electric field is 0, due to the thermal energy, the free electrons of the material may have some velocity which are moving in random direction. Due to the random direction, the vector sum, that means the average velocity of this case will be 0, therefore U average, that is nothing but U vector by n, that is 0 because of the random motion. Now in order to establish the current in the conductor, I can use I can take the help of electric field. Now you see that this is the same conductor, but now we are going to apply some external electric field. So this is positive n and this will be negative n. So we are studied electric field is acting from positive to negative n. Because of that electrons are moving in a specified direction. Instead of random direction, there is a specified direction which establishes the current in the as a conductor. So in this case, I can use the equation of motion, that is V vector, that is equal to U vector plus A vector into T. Average value means we know that. What is average value means? Average velocity, that is V average. This V average is nothing but V drift, that is like U vector by n. Here also I can write V vector by n. Therefore U vector plus A vector T divided by n. Now U by n, you just split that as a division term. So Vd vector, that is equal to U vector by n plus A vector by A vector into T by n. A vector into T by n. Yes. Now you see that this average value is 0. Therefore I can write that as to be A vector into T by n. This term T by n is called a relaxation time tau. Therefore Vd vector, that is equal to A vector into tau. Now this is called tau relaxation time. So relaxation time. Yes. Now I am going to substitute the value of A. Since the electrons are accelerated, so therefore I can say that F is equal to ma vector. F is equal to QE, you are studying in electrostatics. Here the charge is electron, so minus EE vector. So from this I can get that the value of acceleration is A vector, that is equal to minus EE vector by m. So this is the acceleration of the electron drifted in the conductor. Now you take this value and substitute over there. Therefore I can get that Vd vector, drift velocity Vd vector. So drift velocity Vd vector, that is equal to, instead of A I can use that minus EE vector divided by m into tau. I can rearrange the term minus E tau by m into electric field E. So this is the expression for drift velocity. The negative sign represents that the direction of the applied electric field and the direction of motion of electrons are in opposite direction. Or in scalar form I can write that Vd is equal to E tau by m into as E, that is equal to E tau by m into electric field can be written as voltage by length, or that is called a potential gradient. So for some derivation or problem solving purpose, that expression also we needed. Now there is a constant. This constant is called mobility. So mobility called mu, that is equal to E tau by m. So therefore I can write that Vd is equal to mu into E. So there are two expression. One is in terms of scalar, and another one is in terms of vector form, where mu is called mobility of the electron. Now we are going to discuss a basic definition for electric current. Therefore the next is electric current. In general, the value of drift velocity is very less in centimeter per second, or very less in value. But once the switch is closed or a circuit is closed, then how we get the current instantaneously or very immediately means the electric field in this term will exist or move in the speed of speed of light, that we will discuss in electromagnetic waves. So electric current, now we are going to discuss about electric current. Now you please see that there are two kind of definition for that. One is called steady current. I can define this as to be steady current, and another one is instantaneous current. That means steady current means Q by T, that is equal to NE by T. So this is equal to NE by T, quantization condition. Here I is equal to dQ by dt. So what is the main difference between these two means? Here the amount of charge crossing through the given section or area of cross section, that will be constant. But here the number of electrons crossing per unit area will be different. That is the main thing. And you are all very familiar about the unit. So SI unit of current is ampere. So it is a scalar quantity, and you know that generally, even though it is a scalar, we are telling that the direction of electric current is either as opposite to motion of electron, direction of motion of electron, or along the positive charge direction, This is one of the current direction representation. And the second one is from the external circuit, we can say that current is going from positive of the battery to negative of the battery. Therefore from positive to negative terminals of the battery. So these are the two sign convention. Once again I am telling that this is just for convention, but current is a scalar quantity since it is not obeying the vector algebra. Now you please go for the another important topic, that is called another important topic, relation between current and drift velocity. Let us consider the same conductor of length L, which is connected with some battery. This length L and area of cross section as A. Then we know that electrons are moving from negative end to positive end with the constant velocity Vd. Now we please see that by definition velocity is equal to distance by time, where time is nothing but we can write that Vd, so distance by time. This is the first expression. And again we know that by definition I is equal to Q by T, or Q is nothing but Ne by T by quantization rule. Now what I am going to do here is we just multiply by volume and divided by volume. So therefore we know that number density, that is number of free electrons per unit volume, is called number density. Therefore I can write that I is equal to small n E divided by T into volume of the conductor can be written as to be area into length. Therefore area into length. Distance by time is nothing but velocity as per the first equation. Therefore I can say that I is equal to NEA. This term is Vd. So this is the required expression for electric current. That means the relation between current and the drift velocity. The another one what we are going to discuss is a current density. Another parameter is current density. So another parameter is current density. So let us consider this is the given conductor. Yes, okay. So now we consider some area of cross section. Yes. So this is the given area which makes an angle area vector. You know that area is treated as be a vector, and what is the reason that generally we have studied in electric flux concept. Let us consider this is the as a direction of as a j vector along the current direction, and this will be as a theta. Now the current can be defined I is equal to j dot a vector, j dot a vector, or that is equal to ja cos theta, where theta is angle between area vector and the j vector. So from this I can write that, so j is equal to I by a cos theta. So this is the general expression. Suppose area vector makes the angle 0 degree, that means this cross sectional area is perpendicular to the current flow. Therefore in that case theta becomes to 0 degree. So therefore j is equal to I by a, that is current by area is nothing but current density, and its unit is, we know that this is ampere per meter square. So that is the expression or the definition for current density j vector. Next what we are going to discuss is Ohm's law. So Ohm's law, and the next one is Ohm's law. So Ohm's law says that, what it says means at constant temperature, this condition is important, at constant temperature the current produced in or developed in a conductor is directly proportional to potential difference between the ends of the conductor, that is I proportional to V, or I can write that I is equal to 1 by R into V, where this R is called some proportionality constant known as to be resistance. Therefore I can write that V is equal to IR. Since there is a directly proportional to that relation, therefore the corresponding graph will be, so this is the independent variable V and this is the dependent variable I. Therefore the graph will be a linear one since they are directly proportional, and you just to find the slope of the graph theta. So that is a delta I divided by delta V. So therefore from this we can say that R is equal to V by I, that is nothing but as per the graph 1 by slope, that is nothing but delta V by delta I. So this term is called resistance, that is the opposing nature of the or opposition for the current flow offered by the any material due to its the thermal agitation, that is called resistance. That we will discuss again later. And another thing is, now you see that 1 by R, that is nothing but G called conductance. The SI unit of resistance is ohm, and this is ohm inverse. The conductance is the SI unit will be ohm inverse, or we can write like this also. Yes. The next what we are going to discuss is how this resistance of the conductor depends on the external parameters like length and area of cross section. So the resistance R is directly proportional to length. When length increases, resistance offered by the conductor also will increases, and when area of cross section increases, the resistance value, that collision value will be reduces. Therefore I can say that R is equal to some proportionality constant, therefore rho into L by A. This rho is called a proportionality constant. Try to understand, this is the proportionality is a constant. That means whatever change happen in L and A or R, whatever the things happen, changes happen, the rho remains the same. Sometimes they may ask you, when the wire of length L is doubled, what about its resistivity? Resistivity is a proportionality constant, so therefore whatever the change happen in L, A and R, it won't affect the rho value. Yes, that you please keep in mind, and this is very important results. Now next what we are going to discuss is so next topic or subdivision is what we are going to discuss is expression for resistivity. Expression for resistivity. This proportionality constant is called resistivity. So rho, we can call it as that is rho. Yes. Now please see that what is this resistivity means. We know that I is equal to NA E into VD. Yes. This I is nothing but voltage by resistance, that is equal to NAE. Already we derived the drift velocity in scalar form. So this is the drift velocity in scalar form, or this one. Therefore I can write that E tau by m into electric field. Since electric field can be written as to be potential gradient, so therefore this E can be written as voltage by length. Here the L be the length of the conductor, what we are assuming. So let length of the conductor. So therefore this voltage term gets cancelled out. Therefore 1 by R, that is equal to N E square tau divided by M into A by L. Now you please reciprocate this equation. So this is nothing but G, conductance. Now you please reciprocate that expression. That means I can write that the reciprocal of that equation. That is R is equal to M divided by N E square tau. Yes, into what will be there? L by A is there. Now you please take this expression and compare with this equation. Just compare with this equation. That is R is equal to rho into L by A. By comparing these two equations, we can get that the resistivity of the material. Therefore, resistivity rho is equal to M divided by N E square tau. So this is the resistivity formula in terms of microscopic variable, where M is mass of the electron, not for any other thing, mass of the electron. Yes. From this we can say that 1 by rho, that is nothing but a sigma, current conductivity. This is resistivity and that will be conductivity, sigma, that is equal to, you just reciprocate that N E square tau divided by M. So this is the expression what we have. Yes. The another one what we are going to discuss is since we are going to discuss in temperature dependence of resistance category, there how that tau and N value will vary with respect to temperature. When temperature changes, the relaxation time and number density of the material will change, which will affect the value of rho R as well as value of resistance. That we will discuss in separate session. Yes, but anyway, just keep in mind that these values are temperature dependent. That's why here we are using the word called constant temperature. Yes. Now please see that the another one is the relation between current density and the electric field E vector. This expression we have to write. This is called sometimes called a vector form of Ohm's law. That you please keep in mind. So how to derive this expression again means just to see that I is equal to NA EVD. Yes. Now please see that I by A. So I by A, that is nothing but J, that is equal to NE, and VD can be written as E tau by M into capital E. So therefore I can write that J is equal to NE square tau. Yes. N E square tau divided by M into this is E. So just now we said that conductivity is nothing but N E square tau by M. Therefore I can write that J vector equal to sigma into E. This is the scalar form. If you want to write the vector form, we can say that J vector is equal to sigma into E vector. So this is the today's discussion. And you just note down the theory part. So now we see that yes, we discussed that yes, vector form of the Ohm's law. So there are some limitations of Ohm's law. So what is that limitations of Ohm's law means? Before that, you just know that what is ohmic and non-ohmic substances. Ohmic substance means which obey the Ohm's law, and non-ohmic means they does not obey the Ohm's law. But there are certain limitations, even though the material is obeying Ohm's law, that is ohmic substances, and the limitation, the first one, for ohmic substance, even it is ohmic substances which obey the Ohm's law, at a higher temperature, yes, Ohm's law is not followed by the ohmic substances. That is one of the limitation. That means Ohm's law is not valid for all the temperatures. Therefore, for example, this is the voltage and this will be the current I. So this line represents the directional proportional. Up to certain temperature, there is a directional proportional between current and voltage. But when temperature increases, the graph deviates from the linear variation to non-linear variation. That is the one of the limitation. That means even for the ohmic substances at high temperature, Ohm's law is not valid. And second one is, you just consider some substances like semiconducting diode or semiconducting material, the value of or the shape of the graph depends on sign of the potential. Say this is applied potential in positive value and this will be applied potential in the negative value. So in this case, for the diode, if you are seeing that the graph variation will be like this. This is the IF that we will discuss in semiconductor, forward bias current. The variation of I and V graphs will be like this. But for the same material, for the same amount of voltage what we applied, the shape of the graph will be as not very similar to this one. The shape of the graph will be changed like this. That means when sign of applied potential reverse or changes, the variation of current and voltage also will be differ. So that is the another drawback. That means there is no symmetric variation during the positive and negative voltage applied to the system. And the third one what we discussed is there is no unique values. There is no unique value between the current and the voltage for some substances like gallium arsenide. Yes. So in such type of materials, we just see that this is voltage and this will be the current. The graph will be a straight line and it will be changes like this. Up to certain region, that graph will be linear. So up to this region, the graph will be linear. But in the rest of the cases, the graph will be a non-linear variation. Now, we please consider a particular current value. So, let us consider this is some current I, and now we see that for this particular current, there are two different voltages. That means, what is that uniqueness? There is no uniqueness for some materials. There is no uniqueness. That means, for a particular value of current, there will be only one voltage. But some substances like gallium arsenide such type of materials, for a given current, there are two or more voltage values. Like that will be there. So these are some drawbacks or limitations of the ohmic substances. And next, what we are going to discuss is called carbon resistors. Resistors. What is carbon resistor? Generally, resistor means to control the current flow in a given circuit. But when you are using normal resistance made by wire, due to the Joule's heating effect, there is a loss of energy. The applied electrical energy is wasted in the form of heat. And the lifetime of the normal resistor also will be less and more heavy. Such type of drawbacks are there. For that reason, they are using carbon ceramic materials, where this is the carbon resistor. where this is the carbon ceramic layers. With that, a metallic contact will be made as shown in the diagram. Yes. So this is a simple arrangement of the carbon resistor. The resistance purpose is to control the current, but the normal wire made resistance, there are some drawbacks, like its larger size has a loss of energy due to the Joule's effect or heat loss, or we can say that there are a lifetime also very less and more cost like that. So all the disadvantages of wire made resistance are overcome by the carbon resistor, very smaller in size, less energy loss and more lifetime and easy cost like that. So in order to represent this, since their sizes are very small, in order to find out its value, they are using some color coding system. So this is end 1. So let us consider there are three colored rings one side, and another one is only one colored ring will be there. This is called a tolerance value. This is called a tolerance value. And the first value, this is the value of A, and this is the value of B, and the third color represents the power of 10. Yes, power of 10. Say for example 10 to the power of C. For this tolerance value of the any resistor, if there is no color means as a 20%, and silver means is 10%, and gold ring means 5%, like that the deviation will be there. Therefore, the resistance of the carbon resistor can be written as R is equal to AB into 10 to the power of C. That means the third color ring represents the power of 10. And these are the significant digits value. Plus or minus, the tolerance value is denoted by plus or minus, depends on this colored value. So plus or minus R value, that is tolerance value, like 10 or 5% or 20% like this. So for that they are using some color coding system, that is the well known as one. We can write that B Roy of Great Britain Great Britain is very good wife. Okay, so this is black, this is black, the value will be 0, and this will be brown, the value will be 1, and this will be red, the value will be 2, and this will be orange, that value will be 3, this will be yellow, and this value will be 4. B Roy of Great Britain. Yes, so that means is a green. B Roy of Great Britain. So this is a green, the value will be 5. Is a brown, black, is a blue, and 6, and this will be violet. B Roy, BBROY, B Roy of Great Britain, having is good, so that is gray value, and this will be 7, and this will be 8, and this is white, that will be 9. So this is the color coding system. There is some memory trick, that is BB Roy of Great Britain, having very good wife, like that they are giving some memory trick for that. So how to use this color coding to the given resistor? For example, you just consider there is a carbon resistor. Yes, this is the carbon resistor. Yes, now you see that there are certain colors are given. So, and this is the so this is the gold ring, and this may be like a brown, and next is this has to be yellow, and this has to be like green. So such type of colors are there. As we discussed here, we can write now the value of a carbon resistor as, we can write that R is equal to brown. The value of brown is 1, that is like A, and B is yellow. Yellow value is 4 into 10 to the power of C, that is green. The value is 5. Therefore 10 to the power of 5 plus or minus gold ring means 5% of that value. So plus or minus 5%, or the same can be written as 1.4 into 10 to the power of 6 plus or minus 5%, or we can say that 1.4 plus or minus 5% in mega ohm value, in mega ohm. So this is the what is general is a representation how the carbon color coding systems are used. Yes. So thank you, students.